Swayam Prabha. Digital India. Educated India.
So, this way of writing the problem, as I said, is not, this is not well posed here, this is not well posed. So, because this is not well posed, the right way of posing the problem is that we are not looking for actions u0 to u n minus 1, but rather functions. We are looking for functions, and now let me denote these functions in the following way: mu 0 to mu n minus 1, right. So, mu 0 to mu n minus 1 such that the amount of stock to be ordered at to be ordered at time k, which is u k, is equal to then mu k of x k for all values of x k. So, whatever be the value of whatever be the value of the stock available at the beginning of the time period, you will be able to find u k as a function of that once you know mu k. So, what we are looking for are these functions, okay, these functions mu 0 to mu n minus 1, and as a and these functions would then, once these functions are fully specified, what they let you do is pick your action, which is the amount of stock to be ordered, as a function of the information that would be present. So, therefore, the problem, the correct way of posing the problem, the correct way of posing the problem is that you want to minimize the expected cost, includes the terminal cost plus all these running costs starting from 0 to n minus 1 r of x k plus c of u k, and you want to minimize this by choosing mu 0 to mu n minus 1, these functions. So, mathematically this is what is being done. You are trying to optimize this particular cost function now by choosing a sequence of functions. Okay. Now, the reason we needed to do this was because demand itself is something that was going to be realized in the future, all right, and it was not known, its value was not known to us. So, we had to essentially plan for every possible value, and when we are planning for every possible value, what we are effectively doing is finding the sequence of such functions, right. Now, there would be another case, suppose, in which someone told you what the exact demand is going to be. Okay. Hypothetically, say suppose someone gave you the exact value of the demand, in which case the expectation here would be moot, the expectation in this that I have written here would be moot, and then what you would know the exact value of the information or the exact value of the amount of stock that would be present at the beginning of each time period. In that case, you can actually plan to for taking a particular action, because you know the exact state, right. So, there are no, you do not need to plan for every possible state, you can simply try to find the value of each the action for the particular state that is going to be realized, all right, for the or the particular value stock level that is going to be realized. That kind of case where the demand is known would be the case where the noise is deterministic. So, it is really not noise anymore, the demand is deterministic, it is known in advance, its value is known in advance, and all you are doing is planning for specific events that are going to happen in the future, specific known events that are going to happen in the future. That is a much easier version of this particular problem. But the more general version of the problem is involves taking these decisions without knowing what the information is going to be, right. So, this mu 0 to mu n minus 1 that I have written here, this is what is called a policy, okay, and it is often denoted by pi. Okay, so, the distinction here that I have, let me mention one more point here, the distinction between what is called what I have been saying as taking a particular action, which is the amount of stock to be ordered, versus planning for every possible level of stock. The distinction between these two is the distinction between what we call in stochastic control and in games as the distinction between actions and strategy. What we have effectively done is, because we do not know the information that is going to be realized in the future, we are not committing or deciding on what particular action is to be taken. Rather, what we are doing is we are coming up with a strategy which says that, if I had this information, this is what I would do, if I have that information, that is what I would do, right. So, this here, these functions mu 0 to mu n minus 1, they took, or your policy effectively constitutes doing what is called strategy. It involves coming up with these plans, whereas u 0 to u k minus 1, these which are the actual decisions you are going to take, these constitute actions. Right. So, our problem therefore is to come up with these strategies or these policies, right. Now, every time a problem involves noise, whether you however simple or complex the problem the noise may be, the problem shifts from the space of actions to the space of strategies, because we do not know the value of the noise in advance. It means that the action, you cannot plan for any specific actions. So, problem of choosing actions is simply a problem of choosing these vectors, right. So, sorry, this was not k minus 1, this should be n minus 1. The problem of choosing these actions is simply a problem of choosing these n vectors u 0 to u n minus 1, all right, and I can stack them up and essentially think of this as one composite decision problem involving one long vector, right. So, u 0 to u n minus 1. However, this problem here, the problem above, is not a problem of choosing vectors, it is a problem of choosing functions. So, the space of the problem itself has changed. The problem of choosing actions, which is the problem that you would have if say the w's were deterministic, that problem is a problem of simply the problem of vector optimization, whereas this problem here is a problem of optimization over functions, right. It is a problem of finding the right sequence of functions, not just a sequence of vectors. So, this distinction is actually what makes this dynamic programming or dynamic optimization significantly harder than static optimization. All right. Now, as I go a little further, I will explain to you how we can actually reduce somehow this problem, which is involves trying to decide these n functions to a setting, to somehow a setting where we have to decide only actions. Okay. So, actions, but actions and from there, from those actions somehow deduce what the function should be. So, all of that will happen in a subsequently as we go further down in this course. Okay. So, now to summarize what we have said in this example, let me write for you uh, a general dynamic optimization problem or a general dynamic programming problem and its main constituents. Okay. So, the main constituents of a dynamic programming problem involve first a, a state. The first component is the state of the system. Okay. So, the state of the system simply is your xk in this case, which was the inventory level. So, this okay, so it will be denoted by xk. It was in the previous problem, it was the inventory level. It captures, it is whatever is needed, it is whatever is needed to capture the configuration of the system. It is some description that we have of the configuration of the system that we are dealing with. In this case, since the system we were in the example we saw, the system we were dealing with was the inventory in a shop. So, it was enough for us to keep track of just simply the amount of inventory present at the beginning of the time period, right. So, so as a result of this, that we took that as the state of the system. Now, the state of the system is a part of problem modeling. What exactly you want to define as the state? It's a bit of there are usually more than one way of defining the state, but try to always keep the state as simple as possible. For instance, in the previous problem, we could have because we were talking of inventory at and trying to decide the stock over these n time periods, we could have taken the state as the entire history of the stock levels up till time k. Now, that entire history could be taken, but it has no bearing on trying to decide. It does not help in trying to decide what we are actually looking for, which is the amount of stock that is to be ordered, because that the amount of in order to decide what the stock that we have to order, it is enough to simply know what the level of the stock is at the latest time period, not, and the entire history is actually not relevant for that. So, as a result, we have picked a parsimonious definition of the state. We have taken the state as simply the current the level of stock at the current time period. Okay. So, now the state itself, state evolution or dynamics. Now, the state itself evolves based on the action that you would take and the noise that comes up in the system. So, the way we express this is that we write x k plus 1 as some f k of x k comma u k comma w k, right. So, here this is the action at time period k, this here is the noise, this is the noise at time period k, right. And so, as a function of the action that you plan to take at time period k and the noise that evolves at that time period k and the previous and the state at time period k, you get the next state, okay, the state at the next time period. Right. Now, because this W k is random, this sequence will be random. All right. So, the sequence of states will be random. It is not something whose value you would know at the beginning of the time at the beginning of the problem. Okay. And so, as a result, the actions that you will end up taking would also be random, because they would be chosen as a function of the information that you have. Okay. So, this here is these are this is W k is noise. Usually, we take W k as independent random variables. In many cases, also identically distributed or 0 mean and so on, but that depends on the problem. Usually, we take these as independent random variables. All right, and they are independent of each other, and their distribution cannot be decided as a function of using through your actions. Okay. Now, there would usually be a control constraint on actions. So, that constraint on actions is in our case was say u k greater than equal to 0. Okay. So, for example, that was our constraint, but more generally it could be any constraint, and moreover that constraint could depend also on the state that you are in. Say for example, it could be something like this: u k belongs to capital U k of x k. Okay, this would be the most general way of writing the constraint. So, as a function of the state x k that you are in, the kind of the actions that you can potentially take have to be in this set capital U k of x k. Okay. All right. And the additive cost form. The cost form is denoted in this sort of way. Here is your terminal cost g n of x n. Remember, we are taking actions starting at time 0 till time n minus 1. The problem ends at time n. So, at time n, whatever is the state, based on that you incur a terminal cost g n of x n. We are not taking any further actions at time n. So, although I am saying, I have said that we take actions at n time instants, the n time instants themselves are denoted 0 to n minus 1. All right. So, this is, so the entire cost is therefore g n of x n, which is your terminal cost, plus g k of x k u k. Sometimes we also include w k here, but it does not matter, d k u, it can this inclusion here is optional. It is, you can simply write g k comma u k, that is also without loss of generality. All right. So, as you can see, we are in the earlier in the problem above, g n of x n was, this was simply r of x n, and g k of x k u k w k, this was r of x k plus c of u k. Okay. All right. Now, okay. So, having formulated this the basic problem, then our goal becomes the following, that we would like to decide a policy. So, we would like to decide a pi, which is denoted by mu 0 to mu n minus 1, what we would policy mu 0 to mu n minus 1 such that it would map the state to control actions or to actions that you want to take. Okay. So, u k would be equal to mu k of x k for all values of x k, for all values of k, right. And now, moreover, this kind, now what kind of policies are admissible? Now, remember, since we mentioned we have constraints here on control actions, that control actions needed have to satisfy this particular constraint. The kind of policies that are admissible are, an admissible policy is only one where an admissible policy is one which is in which u k or in which mu k of x k always belongs to u of capital U k of x k. So, this is true for all k comma and all k. So, an admissible policy is one which satisfies the constraints, the control constraints that we have. So, now so how does the problem begin? The problem begins with an initial state. So, you are given an initial state, okay, which is say the inventory level at the start of the time horizon, say an initial state. You given that initial state, you would then and given the initial given a choice of a policy, given an initial state and a policy mu 0 to mu n minus 1, given the initial state and a policy, how does this system behave? Well, it takes the initial state, uses the policy at time 0 to decide the action to be taken at time 0, right. So, it takes the policy at time 0 to decide the action to be taken at time 0, which is, that would be u 0. U 0 then feeds into the state dynamics, and what we get from there is that you get the state at time 1. So, you get more generally x k plus 1 at time k, a time x k plus 1 emerges as a function f k of x k and u k, where u k itself is just simply mu k of x k, right, and the noise w k, right. So, because you are choosing now the action as a function of the state, okay, because u k itself is being chosen as a function of the state, you can now substitute this here, and what you find is that the next state comes up is defined through the dynamics and the policy that you have chosen, that which is mu k, right. So, after this substitution, essentially what one can do is you can do this substitution not, everywhere. In fact, you can do this substitution even in the cost function. If your cost function was g n of x n plus so g n of x n plus g k of u k w k. So, I have replaced the u k there by simply mu k of x k, right. So, as you can see, the cost function now depends on two things. So, this depends on pi, which is your policy, and depends also on the initial state. Okay, it depends on where you are starting, because after all the state evolution that your system would see would now get determined by the dynamics and the policy that has been stated. So, once I fix my initial state, which is the state where I am starting from, and the kind of policy that I have chosen, the noise distribution is what will determine the evolution of the state sequence. Okay. And so, what we have therefore is the expected cost of the associate of evaluated over this particular noise sequence, and that depends, as you can see, on pi as well as x 0. So, we denote this therefore by j subscript pi of x 0. So, this is therefore, this is what is this quantity? This is the cost incurred by policy pi starting from state x 0. That is what this would be. So, what is therefore the problem? The problem then the problem that we want to solve then is to find policy pi star in, say, a space capital pi. Now, what this capital pi here is the set of admissible policies, set of admissible policies sorry j pi star such. So, find a pi star which is in the set of admissible policies such that the cost of the cost that you incurred by pi star is the least amongst the cost of all policies in the set of admissible policies. Okay. Now, the cost the notice that this is it appears like this particular problem is actually a problem that we would now need to solve for each value of x 0, because we have not gotten rid of the initial state as yet. So, we would have a cost for each initial state, and it appears prima facie that the pi star, which is the optimal policy, could vary with x 0, because I have just fixed one x 0 and found a pi star. However, the nature of the problem is such that it turns out that it is typically possible to find a pi star that does not depend on x 0 itself. So, you can choose any token x 0 to start with, and the policy that you would find, you end up finding a policy that would work for any initial state. Okay. So, that is how it often happens. It is because the policy itself is something that is a plan for every possible state. So, it does not it's not merely for the specific state that you are looking for. You usually get the policy for every possible initial state. So, this particular quantity, which is the j pi star, this is also denoted by j star of x 0. This sometimes denoted by j star of x 0, that is simply another way of writing the cost of the optimal policy. This has a name, it is what is called the optimal value function, optimal value function. So, the optimal value function is simply a function that tells you what the optimal value of the dynamic optimization is going to be as a function of the initial state. Okay. This is called the optimal value function or optimal cost function. Okay. This optimal cost as a function of initial state. Okay. So, this is so what we will now what we will do in the next class is find ways of computing this particular the optimal value the optimal value function. Okay. So, I will pause here and we will resume again in the next class.